Alright, hey guys, so today we'll cover decision trees and why decision trees are important, and actually it's a step-by-step guide so it helps you understand the fundamentals much better. So let's go to the agenda. So the agenda, we talk about some data preparation, then we talk about the different splitting mechanisms you can do, where you can use entropy or Gini impurity for classification models, and then for regression it's variance reduction. And choosing the right split, that a bit about the recursion of decision trees, and then also the how predictions are made, and then a quick summary of that. So let's dive into the data preparation. So overall you have a data set, and each data set has got a bunch of features. We label them big X, and then we have an output which is Y. And if Y is a category, we are solving a classification problem. And if Y is a number, then it's a regression problem. That's quite important to know because it's different splitting mechanisms and then different ways to get the predictions out as well, which we'll dive into in a bit. Now we go over our first splitting mechanism, which is entropy. So this is the formula of entropy, and where C is the number of different classes you have, and P1 is the proportion slash probability of that class. Then we have the entropy after the split here, which looks like this, where D is the split, and then it's splitting into K subsets. And then we have the information gain. So this is the information you get from the splitting as well. And so the idea of the splitting is you want to keep it as data as homogeneous as possible, so making sure that the same classes are split into the same groups, if that makes sense. And so here, let's go through an example data set where let's say we have a simple binary data set, and we have 10 examples. We have 6 positives and then 4 negatives. And now we're going to go through the steps above here to figure out. So first we're going to compute the overall entropy. Let's get that out. So first we're going to compute the overall entropy. That's the formula. The proportions for positives are 6/10. The proportions of negatives are 4/10. You plug it into this formula here, which is basically the same as that, and you get around 0.971 bytes. Now then we're choosing the splitting feature, so we take a feature from X, the one feature, and then we create a split of the data set. So here, let's say the subset is D1, and where X is equal to yes, and then we have 4 examples, so 3 positives, 1 negatives, and D2 where X is equal to no. So that's one particular feature, where we have 6 examples, 3 positives, 3 negatives. Now we're going to compute the entropy for both of them again. So for D1, it's the proportion is 3/4. For positives, for negatives is 1/4. Because we only have 1 negative out of 4 samples and 3 positives out of 4. 4 examples. That gives us the entropy, which is here once we plug it into the formula. Similar thing with D2, where we have 3/6 positives because it's 3/6, and then also 3/6 negatives. We plug it in and we get 1 byte out. Now the next step 4, is where we compute the weighted entropy, which is in this formula, and we plug it in a bit. So it's D1 has 4 data points, and D2 has 6 data points, and D has 10 data points. So we just put that in, get our proportion value out. And last but not least, we calculate the information gain. So the information gain is when we get the original entropy value and then minus it with the split. So we do this and we get that as a positive value, which means there is a more information can be gained after the split because it's more homogeneous. There's more, it groups the data much better after the split as opposed to not splitting it. So that's that, and that's pretty much how it goes if you use the entropy as your splitting mechanism. Now we can also use something called Gini impurity, which is very similar, and we're doing more or less the same thing. So here it looks like this. So it's 1 minus the summation of 1 to C, where C is the classes and Pi are the proportions of these classes, and then the weighted Gini for splitting. So here we have the same example we're doing, 10 samples, 6 positives, 4 negatives. We calculate the overall Gini impurity, which is put here. Then we are splitting the data exact same way as we did before, just for the sake of simplicity, where we have 4 examples, 3 positives, 1 negative, and then we compute that particular Gini for each of those as a subset of data. So that's for D1 and D2. And you can see that for D1 we get this value out, and then for D2 we get 0.5 out. Fantastic. And now again we calculate the weighted Gini impurity, which is here. Again, that's very similar to the one we did for entropy, and we are doing 4/10 times 0.375 because that's that's what we get for D1 here. And then we do 6/10 times 0.5, which is what we get from here, and we get 0.45. Now we do a bit of interpretation to help you out. So the Gini impurity was 0.48, but now after the splitting is 0.45, which means it's been reduced by 0.03, which is great because it helps you keep the data more pure, which is the whole purpose of splitting. Now this is all for classification. For regression models, we have something called variance reduction, which again is very similar here. It looks like this, and then we have something like that. So do pause this video if I'm going too fast. And here again we do a quick example where we have different target values. So we have 10 data points, and that's how the different target values for those 10 data points. We get the mean out, then we get the variance out. Fantastic. Then we split the data. We get the mean out for the splitted data, and then for D1 and then D2. We also then get the variance out because you need the mean to calculate the variance. So each of them is 2. Then we calculate the weighted variance, and we get that value out too. And now we're looking at the variance reduction formula, which is 8.25 minus 2, which is 6.25. And that's all it is. And then the overall conclusion of that is that, yes, our beginning of variance was 8.25, but now each of the subsets is 2. So we got a reduction of 6.25. Which is great because that means if the variance is low in your dataset, that means it varies less, so there's less spread with your target values, which is what we want. And yeah, that's pretty much all. Those are the 3 main splitting criteria. So yeah, how we choosing the right split. So actually what the computer does is, the algorithm does is, for a particular feature, it computes all those different splits and then chooses the correct split to maximize your information gain. So that is your entropy or your Gini, or it maximizes your variance reduction, depending if you have a classification model or a regression model. And now this what we covered was only one split. Now, once we split the data, which is, let me show you, there's a picture at the top. So once we split the data here, it keeps doing it recursively. So we do the exact same splitting at this node here and then at this node again here as well. So let me find the slide. So yeah, we keep doing this recursively, and there are certain stopping criteria which can be done, which can also be in your hyperparameters, such as having a maximum tree depth. So tree can only be like, let's say, 3 levels deep, and then you stop it. Or you can have in your leaf node, so that's the final node, have a maximum number of samples. Or what you can also do is that if there's no improvement after the splitting, then it stops as well. So there are many different stopping criteria, which is good, and it helps deal with overfitting as well. Now that's great. So once we are at the leaf node, how are the predictions actually made? So let's say we have the data. Now we've got ways to split the data. We get new data. It goes through the whole decision tree. How are the predictions made? So yes, it traverses through the whole tree until it gets to a leaf node, and then for classification, it traverses through a whole tree until it gets to the leaf node, and then it looks at something called majority voting. So let's say the leaf node still has, let's say, 8 negative samples but 2 positive samples. But because 8 is bigger than 2, it gives the prediction of 8, which it gives the prediction of negative samples because it has a higher value. Or another example is the majority voting could be like, let's say you have at the leaf node you have 30 positives and then 20 negatives, and because 30 is bigger than 20, it will give a positive prediction out. Now in regression, it does something similar where it goes through the whole tree, it traverses the tree, and then at your leaf node, it just samples the remaining target values of your data. So let's say you have some data left, let's say 1, 2, 3, and then it takes the average of those and gives you 2. Yes, it should give you 2, I think. Yeah, it just gives you the average of that. And that's all it is really. So that's all we talked about. So we talked about the data preparation. We talked about all the main different splitting criteria. There's entropy, then there's Gini, and for classification, and then for regression, it's variance reduction. We talked about how the splits are made. They're actually computed already by the computer to get the right threshold. This is then done recursively, and then we also talked about how the predictions are made, where you traverse through the tree and then you either do a majority voting or you calculate the average if it's classification or a regression model. One thing I also wanted to say is that some machine learning models, decision tree models, they have entropy as the default splitting method, and then others actually have the Gini impurity. I think some models in R has it in Gini impurity, and there's some pros and cons to that, such as entropy. It uses the logarithms, and some people may not like using the logarithm, so they want to use Gini. And then the Gini is more computationally efficient because a bit less maths needs to be done. And that's all from my video, guys. Thank you so much for listening. I hope you enjoyed it.